In this module, we're going to be considering vector components and unit vectors. The idea of breaking a vector into components is really nothing more than reversing the notion of vector addition. That is, we can consider any vector to be the sum of some number of component vectors. Now, clearly, this idea isn't useful unless we have some rules about how we decompose a vector. In 2 dimensions, we decompose a vector into 2 linearly independent component vectors. In 3 dimensions, we need 3 linearly independent component vectors, and so on. 2 vectors are linearly independent if they are not parallel to each other. While not necessary, the simplest thing we can do is to choose the linearly independent vectors used to decompose the vector to be orthogonal, or that is, perpendicular to each other. We can understand how all of this works by looking at examples in 2 dimensions. The simplest approach is to decompose vectors into components that are parallel to the Cartesian coordinate axes. So in this case, our vector A is decomposed into 2 vectors, one which is parallel to the x-axis, a sub x, and another which is parallel to the y-axis, a sub y. Now, if we consider the magnitude of each of these vectors to be expressed by simply writing the same symbol down but not putting the vector arrow over top of it, and if we let theta be the angle between our vector and the x-axis, then we can write the magnitudes of the components using a little bit of trigonometry. The x component, ax, is going to be a times the cosine of theta, and ay is going to be a times the sine of theta. And of course, if we have the components a sub x and a sub y, we can use the Pythagorean theorem and a little bit of trigonometry to find the magnitude of a and the angle theta. We see that a 2-dimensional vector needs 2 pieces of information to fully describe it, either the magnitude a and the direction theta, or 2 scalar components a sub x and a sub y. Both descriptions of a also require an understanding of some default direction, like the direction of the x-axis. We have to set up a convention. It is conventional to have the x-axis horizontal and the y-axis vertical, but you can choose how you want to have how you want to orient the coordinates that you use to define the vector components or direction angles. So we could rotate our coordinate system in the following way, and we see that when we do this, the components of the same vector A are now different because the directions of the x and y axes have changed. Now, a convenient notation is something called unit vector notation. The vector ax has magnitude ax and points in the direction of increasing x. So a convenient notation is to define this vector as the component ax times a unit vector x hat, which points in the direction of increasing x. So in general, we could write our vector a as the component ax times the unit vector x hat plus the component ay times the unit vector y hat. A unit vector is an ordinary vector with a special property that it has a magnitude of 1 and has no units. The only useful information it carries is its direction. Most common are the Cartesian unit vectors. There are multiple conventions for their names. The most common are using x hat or I hat for the unit vector pointing in the direction of increasing x coordinate, for the y direction, y hat or j hat, and in the z direction, z hat or k hat. And we will actually primarily be making use of the I hat, j hat, k hat notation. So let's look at a few examples. The vector x we've seen we can write as the x component times the I hat unit vector plus the y component times j hat. This is just a general vector. Let's consider gravitational acceleration in the vertical direction. Let's let z be the axis which points up. Then the acceleration is going to be given by minus g times k hat. Or if we want to use actual numerical values, it would be minus 9.8 meters per second squared times our k hat unit vector. And we might consider a displacement in a combination of the x and y directions as 1.50 I hat minus 2.70 j hat times the meter unit, so that the x component of the displacement is 3.5 meters, and the y component of the displacement is minus 2.7 meters. The symbol or number preceding a unit vector is called a component of the vector. So x hat is the x component of A, and minus g, or minus 9.8 meters per second squared, is the z component of the acceleration A. The direction of each component is a combination of the sign of the component and the unit vector itself. So we say the acceleration A points in the minus k hat direction, which is down in this case, and we see that dy, which is minus 2.7 meters, tells us that part of the displacement d points in the minus j hat direction. Addition of vectors is easy when we use Cartesian unit vectors because each unit vector points in the same direction regardless of where we place the vector. Now, this is an important warning. This is not true if we use non-Cartesian unit vectors. So keep this in mind. Only do the following when we are using Cartesian unit vectors. Adding two vectors which point in the same direction yields a vector that points in the same direction. So if we add the x component of A times I hat plus the x component of B times I hat, we get the sum of the x component of A and the x component of B times I hat, because the direction of I is the same no matter where we place I in the Cartesian coordinate system. We can simply factor it out because it's the same vector in multiplying each of these components. So if we have our two vectors A and B written in terms of their x and y components, we can add them together by taking the tail of B and putting it at the head of A, decomposing each in terms of its components, grouping together the components which are in the x direction or in the y direction, and adding these up, factoring out the unit vectors, and we get, in the end, the components of the sum, which we're calling C in this case. If we do this in terms of some actual numbers, let's let A be 2 meters in the x direction, minus 3 meters in the y direction. Let's let B be minus 4 meters in the x direction and 7 meters in the y direction. Then adding these together, taking a few steps to do this, we find that the result is minus 2 meters in the x direction and plus 4 meters in the y direction. And we can, of course, convert these components into magnitude and direction notation, our magnitude of A and the angle theta between the vector A and the x-axis. And we can, of course, do this for not just A, but for the B vector and the resulting C vector. And with these, it's very important to remember that if you are given vectors in terms of magnitude and direction, you can't simply add the magnitudes and add the angles, or even try some clever combination of adding the magnitudes using some version of the Pythagorean theorem to try and get the resulting value for the magnitude of C. This doesn't work because A, B, and C in general are not going to be the legs of a right triangle, so the Pythagorean theorem simply doesn't apply. And you can't simply add the angles for A and the angle for the B vector to get the angle for the C vector. Now, it is possible to use the laws of sine and cosine to correctly add the magnitudes and the angles together, but this is rather complicated, and I don't advise you to try and do this unless you have a very good understanding of how the law of sines and cosines work.